Lesson 2.5 on angle relationships. Now, back in lesson 1.5, we learned about special types of angles, particularly linear angles. Now, for a quick review, linear angles are two angles that are joined at a common vertex and side, and their non-common sides form a line. Now, not only was that definition helpful in allowing us to clearly define and understand what linear angles were, but now it'll also play an important part in deductive reasoning. But we'll see that in a moment. For starters, though, let's actually analyze this definition. In this definition, there are some important facts. First, there are two angles. So, for example, there you can see two angles. But not only in this definition are there two angles, but these two angles have to be joined at a common vertex and side. So if we take one of those angles, slide it up next to the other, so that they share a common vertex point and side, now we have ourselves a pair of linear angles. But there was one other crucial component of this definition as well. These two angles that are joined at a common side and vertex have their non-common sides form a line. Now, those facts play a particular importance in deriving a conjecture from the definition of a linear pair of angles. So let's think about this. If two angles form a linear pair, then what can we conclude? Remember, most conjectures are written in if-then form. So if we begin with the fact that two angles do form a linear pair, then what can we conclude then from that? Well, let's do some reasoning. Now, we just went over what linear pair was and the facts that make up the definition of a linear pair. So if we analyze those facts for a moment, we know that in a linear pair, the non-common sides form a line. All right, that's established. But we can also pull up as a fact that the angle measure of a straight line, as we've measured before with the protractor, is 180 degrees. Given these two facts, that the non-common sides form a line, and that the angle measurement of a straight line is 180 degrees, we can come to an important conclusion. So in a linear pair, what must the measurements of those two angles add up to? Well, the answer is 180 degrees. So our linear pair conjecture says if two angles form a linear pair, then the measurements of these two angles add up to 180 degrees. Now, we can find more conjectures to use than just with linear pairs. If you remember from lesson 1.5, there was also another special pair of angles called vertical angles. And there's a very important conjecture that goes along with vertical angles as well. In fact, even more important than the linear pair. So let's think. If two angles are vertical angles, then what? Well, again, just like in the last slide, let's do some reasoning. Now, remember for a moment that linear pairs or linear angles are two angles that are formed when lines intersect. These two angles here are linear angles, the angles opposite each other, as well as this pair of angles here and here, angles opposite each other when two lines intersect. So we know that vertical angles consist of two straight lines. In addition, from the last slide, we just discussed that a straight line, i.e. a linear angle, has a measure of 180 degrees. So each of these two straight lines that you see here that are being highlighted have measurements of 180 degrees. Well, from those two facts, we can then conclude that each of these straight lines that have just been drawn are equal to each other in measure. Each of these linear angles are equal to each other in measure because they're both 180 degrees. Now, another fact that we can include is that the two linear angles intersect and share a common side. Share a common angle. Again, as you'll notice, if we shade this straight line and then that straight line, you'll notice that together these two lines share a common wedge. So, if each straight line has an angle measure of 180 degrees, and these two straight lines also have an overlapping section of their angle measurements, if we take this shared wedge away, then what remains must still equal each other. So if that shared portion gets subtracted from the remaining measures of each angle, those remaining measurements must still be congruent. It's just like algebra, where if you actually have a common factor being added to both sides, you can subtract that common factor, and then what's left still must be equal to each other in value. The same is true with this geometry. So, the vertical angle conjecture says that if two angles are vertical angles, then the angles must be congruent. And just to highlight that once more, anytime you have a pair of vertical angles, anytime, always guaranteed those angles will be congruent. Now, what about the converse? Well, what is a converse? The converse is the reverse statement of a conjecture. In other words, remember that a conjecture is typically written in the form if something, then something else. The converse is where we actually take the if and then parts of the conjecture and swap them. For example, we just got done talking about the vertical angle conjecture. If two angles are vertical angles, then the angles are congruent. A converse statement will actually take the if and then parts and swap them. So that then the converse statement becomes if two angles are congruent, then the angles are vertical angles. Now think for a moment. If a conjecture is true, must its converse also be true? Now in this statement, I hope that you can see or think about two angles you've seen before that are congruent that were not vertical angles. In fact, there are plenty of congruent angles that are congruent but not vertical. But that's not to say that no converse statement is ever true. Many of them are, just not all of them. Thus concludes today's lesson.